Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper, Charlie to friends, and I'm a theoretical physicist currently doing a postdoc at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, cool stuff happening inside the universe. I love being a scientist. It really is an amazing job. Most of the time, has ups and downs, but it is overall a really fun job. And I love chatting to everybody about all of the cool things I get to work on. So for anyone who doesn't know this stream yet, the idea here, this is an interactive stream. The idea here is that you people can ask me anything you want about cosmology, about astrophysics, about space, about time, about physics in general, about academia, about myself if you want. It's an ask me anything. You can literally ask me anything you want. I might not answer some of the questions, but you can really ask me whatever you want, and I will do my best to try to answer. If you're a first-time viewer, welcome. I hope you enjoy it here. If you're a regular, welcome back. I see we have some of the regulars coming in, Scott and David Howden. Great to see you. Welcome back. As always, really nice to see you here in the comments. So if you haven't done so yet, please do click the subscribe button, like this video, leave a comment, press all of the usual YouTube stuff. It really, really does help boost engagement, and I really do appreciate when you all press buttons and make stuff happen. Hey, John, great to see you as well. Mito, great to see you. Great to see everybody joining, all of the regulars coming in. So first things first, some of you might have noticed, depending on how good your memory is or how good your visual memory is, my camera looks different, my setup looks different. That is absolutely correct. I have finally joined the 21st century, and I finally have an external monitor, which it's the first time I've actually owned an external monitor. I have them at work, but it's the first time I've had one at home because I moved country so much, it just never made sense. Because it's a big bulky thing that I have to move country with. So I've never had an external monitor of my own in my own place. I finally changed that. I finally decided, I'm happy here. I'm not moving anytime soon. So I have a new monitor, which means my camera has now moved up because it used to be sat on the laptop kind of down here. Now it's up there on top of this slightly insanely big monitor. So the camera angle's different. The lighting is slightly different because I've had to move some things around. So let me know if it's working. Let me know if you want any changes. If there's too much white space, if there's too much of this, let me know. This is literally set up yesterday evening. So yeah, there's still some tweaking to be done. Let me know if it works, if the lighting's okay. I'm not sure how flattering this lighting is for me because it's now off to the side instead of directly behind the camera. Now, if I look at the screen, I am not looking at the camera, so I need to remember to look up there and not down here. So, let me know if it's working for everybody. Let me know if you want changes. Let me know if the audio is still okay. Whole new setup, new microphone, things changing. But hopefully it's all okay. In answer to your question, David, that the walls seem less decorated, that is partly true, but also not completely. The wall is still decorated. But I used to have my back to that wall, and that wall still has the pretty map up there. That used to be a Doctor Who image, then changed to a map. That's still up there. So you used to see me, my back to that wall. I was facing that way, but that way is actually my hallway, and that way is my main window. So now I'm actually facing my window. I get more light. It's a bit nicer. But yeah, it means this wall behind me is rather empty. That is going to change. There is one picture that I still need to put up here. I actually have a really cool antique map. It's a map of, it's a ridiculously nerdy thing that I acquired in an antique shop. It's a map of the public transport systems of 4 major European cities over 100 years ago. And this map is actually from an ancient archive. The map itself is over 100 years old. And it is very cool. And I have a frame for it. I just haven't got around to very carefully putting this in the frame and putting it up. So that is going to happen. And at some point, you'll see this very antique, nerdy public transport map, which definitely is very on brand for me, but yes, very much a nerdy thing. Also, I'm probably going to move one of my plants. So one of my plants will be here at some point. Depending on how things go in the future, there might be a different type of ornament here, or a different type of thing here. We'll see. But yes, I agree that this here needs a bit of decoration. I tried to put black hole in view, but it's just a bit low down, so you can just see the accretion disk. But yes, I will figure out the background. I see a comment here saying, thank you, Beth, for congratulating me on the tech upgrade. I look more like a professional streamer now. That is good. That is good to know. I guess, I'm not sure if I count as a professional streamer or as an amateur streamer, because I purposefully don't get paid to do my streams, so technically that makes me an amateur. Although on that note, there is always a Ko-fi link on the YouTube description where you can buy me a cup of coffee if you want to, and that does help me cover the cost of running the streams. Obviously, no pressure. Cup of Cosmology is and always will be free. So yeah, I'm not sure at which point you count as a professional streamer. I mean, I am almost 9 years into the streaming journey. Does that count as professional? It's always an interesting question, but at least now I have a professional looking setup, so that counts as something. But yeah, it is coming up to 9 years of Cup of Cosmology. So my first stream was in the middle of August in 2015, which was 9 years ago. So yeah, it is very much coming up to 9 years of streaming, 9 years of Cup of Cosmology. Of course, it wasn't called Cup of Cosmology back in the Periscope days, but it is coming up to 9 years, and that is very impressive. And again, I'm just very grateful to all of you who have made this happen and who are still tuning in. But yes, I digress. As often is the case, when do I not digress? Digressing is literally what I do. It's what the stream is about. Me digressing about random topics. Yes. Scott, you made your comment if that's why you never went into repairing elevators or lifts because the job has too many ups and downs. I appreciate the pun. Thank you for that. Okay, so as always, this is an interactive stream. You can ask me anything you want. You can throw ideas for what you want on the walls behind me as well if you want. I might take some of them into consideration. 9 years is too much to be called amateur. Yes, thank you. If we're basing it on years of experience, then I am a professional streamer. If we're basing it on am I getting paid to do this, then no, I'm not a professional. But yeah, give me ideas, or if you want something special back here. I could recreate what I had in my bedroom when I was in my university in my first or second year of undergrad, where I painted my bedroom wall with about 16 of my favorite equations, and I kind of stenciled them out in cardboard and painted them on the wall, which I thought was a very cool idea until we moved house and had to get rid of it, and then painting over that was less fun. But yes, I probably shouldn't paint some equations on the wall. That would be very nerdy, but maybe I'll do something to make this a bit more visually interesting, so you're not just stuck staring at me. There is some random stuff up here you can stare at as well, but there will be stuff around. Stuff's going to appear at some point when I have time to it, gradually. I can say I'm a professional cosmology streamer, just be ambiguous which word the adjective refers to. Yeah, I'm a professional in some things. I'm a cosmology streamer. I am also a professional. At least that's what I get people to think. I'm not sure how valid that is. I'm definitely a professional in some things. I'm definitely not professional in other things, but that's okay. I'm in a job where I can get away with that, which is always fun. So quick announcements, because I've been promising some streams. So got some smaller quick announcements to do. Just see a comment here from David Howden. In the natural history world, some of the greatest experts are amateurs, so I don't see the word as indicating anything about level of experience. Yes, I completely agree. I also, I am being pedantic here with the words when applied to myself, because that's always what we do. We're our best critics. But I absolutely think you don't have to make money off of something to be considered a professional at it. If you enjoy it, if you're good at it, even if you just enjoy it, you don't, making money off of something is not the reason for doing it. And I very much think people should just do things just for the sake of it, and words should have whatever meaning we kind of want them to have. It's always the thing of, the question that comes up often is, at what point do you call yourself a scientist? Do you call yourself a scientist once you're paid to do science? Or do you call yourself a scientist once you're actively applying the scientific method to do research? And I think it's the second one, because we have bachelor students, we have undergrads, we have master students who are not paid for their science, but they are contributing to the field, and they are scientists. So yes, you absolutely do not have to be paid for something to call yourself a professional. So yes, I know I'm contradicting, but what I say about myself is not the same as what I say about everyone else, because that's absolutely how that works. Okay. Is the red black object the black hole question? It is indeed. It's a black hole white hole thing. Now, the only reason this lived on my desk before is because it was the perfect size, because of this part down here, or this part here, where I could cover cables. Like, all of the cables were just slotted neatly down there, and then they were out of sight. So this has always been my cable hider. Now the cables have moved to the floor and I need a better system. So this person, this black hole, white hole has lost its job as cable hider. So I need a new placement for it. Haven't yet figured it out. Right now, it had moved to the sofa. I literally just moved it back here so that then I have it within reach in case someone asks me a black hole question during the stream. Then it's there. Okay, I see a question that involves the word CMB. Excellent. We'll get to that. But first, some announcements. So about a month ago, or 6 weeks by now, I put out a new paper. And I have been saying for a while that I'm going to do a stream specifically about this paper at some point, all the ins and outs, what we did, what we found. That is currently on pause for at least 3 or 4 weeks. The reason being, one of my collaborators may or may not join, still unclear, but they've just gone on holiday. They'll tell me in 3 or 4 weeks if they're joining. So I'm waiting because it's worth waiting in case they do join. So that one's on pause, but it's definitely going to happen. The second one, next week, there is going to be a special topic. So next week, I want to tell you about one of my favorite things, which is perturbation theory, which sounds very technical, and it is, and we're going to do it without equations. So perturbation theory is basically answering the question of why does the universe look the way it does, or more specifically, why does the cosmic microwave background radiation, this amazing map that we have here, oh, this looks so nice on my new screen, this nice map that we have here of the oldest light in the universe, it has hot spots, it has cold spots. And I've always given you a short explanation. You know, there was light in the early universe, there were protons, there were electrons, there were neutrons, sorry, not neutrons, protons, electrons, photons, particles of light. As the universe cooled down, protons and electrons joined together, photons broke away, producing this light. Okay, and the tiny ripples, I normally just say there were overdense regions, underdense regions. That's great. Regions where there were more density, the photons had to climb out. They lost more energy. Today they are less energetic, so they appear bluer here in the night in this picture, and so on. Hey James, great to see you. Welcome. You're not late. You got in time just to see the CMB, so that means you're perfectly on time. But the question that I don't really answer or haven't gone into detail before is what caused these overdensities and these underdensities? Why were there regions that had more photons and protons and electrons and regions that had fewer? Where do galaxies come from? And the answer to these two questions is actually the same. And to answer those questions, we need something known as perturbation theory. Now, this is something that is a difficult topic to cover. And when I've taught this before during my undergrad, I participated in the course Perturbation Theory. It's an 8-week-long course aimed at master students. It is something that is extremely rich, and it's one of my favorite topics, and it was basically the underlying theme of my PhD thesis. So my PhD branched out to a lot of topics, but the general backbone was perturbation theory. So next week, we're doing a perturbation theory special. I have not yet figured out how I'm going to explain things, what I'm talking about, but it's happening next Sunday. So next Sunday, there is a topic. It is going to be perturbation theory. Then the following Sunday, there will not be a stream. That is Sunday the 4th of August, I believe. First, second, third, fourth, fifth. Sunday the 5th, I could just open my calendar. It's literally right here, easier. Okay, so today is 21st. This means that on the 28th, we get perturbation theory. On the 4th of August, there will be no stream because I will be in a different country again. But then on the 11th of August, we should be back. So we're only going to miss one this time. But first, next week, perturbation theory. I am looking forward to it. Bring all your questions. I know if you don't know what perturbation theory is, you might not have questions ready yet. That is perfectly fine. I'm sure you will have questions during the stream. I will do my best to try to answer them. I am looking forward to that because that is going to be a fun stream. Okay, let's see. Comment from David Howden here saying, don't put all your cables in a black hole. You'll never get them back. That is very true. Although, to be fair, what I've done now with my cables probably should be thrown in a black hole, because now I have my monitor, I have my camera, I have an external keyboard and mouse, I have my headphones, and of course an Ethernet cable. So literally all of my ports on, I don't yet have a docking station. So every possible port on my laptop is occupied, and all of the cables are just like thrown in that general direction, like, need to fix that. Yes. Can I spell that theory, please? Yes, that is perturbation. Like when something is perturbing you, like it's disturbing you, that is perturbation theory. So I'm just writing a comment here so that you can, they should appear on YouTube. I'm not sure if I can send it to Twitch. And of course, I misspelled the word perturbation. Let me see if I can spell that properly. Perturbation theory. You should now see this on YouTube. And let me just send the same thing to Twitch, just in case there's people watching on Twitch as well. Because I'm in Restream, so I can send the comments to both. There's the title of what's happening next week, perturbation theory. That is going to be, you should have it here in the comments. Feel free to look it up in advance. It's obviously perturbation theory in cosmology. You might find other perturbation theories, but that is the topic of next week's stream. You just got recommended this live and you watched the movie Contact. Excellent. That is very cool that you watched the sci-fi movie and now you're here learning about science. Amazing. Welcome. Hope you enjoy it here. If you have any questions, feel free to ask. I will try to answer any questions you have. I'm very much glad that YouTube thinks that if you watch Contact, you should come to my stream. I love that. That is very accurate. Okay, so John had a question about 10 minutes ago that I should answer that I just saw the word CMB in, but didn't quite get to yet. Whew, am I talking quicker than usual? I feel like I'm in one of my hyper modes and speaking even faster than usual, but you're all used to that by now. But maybe let me get a drink, catch my breath, and then we jump into the first question that we have here, CMB related. And I should drink my tea at some point. The problem with having a new setup on my desk is everything has moved. Like my monitor's now here, which means the spot where my tea mug used to be is now, everything's moved. My tea is now over there, my Porsche's over there. I haven't yet figured out optimum placing for things. This is an ongoing process. Question from John. Plan was to catch my breath. I did not succeed at that. Question from John here. I have a question about scale and the CMB. Could you give me an idea of how big the area of the CMB is that would develop into a supercluster like Laniakea? Love that. So Laniakea is our kind of local area, our local network, where our galaxy is embedded within so our galaxy, Milky Way, is embedded in a big cluster of galaxies known as the local group. This local group is embedded in part of a network, and this forms Laniakea, which is like our local area of the neighborhood. I'm talking quicker, but I just thought it was time dilation from the black hole plushie. Yeah, exactly. Black hole plushie next to me, time dilation. It sounds like I'm talking quicker. I'll blame the black hole plushie. Okay. So the question, hey Arlo, great to see you. Not sure if I've seen you here before. Great to see you. Welcome. Feel free to ask any questions. I love the little image you have. I just see planets and black holes there. Very cool image. Okay, so this is the CMB, the cosmic microwave background radiation. Now this map is always a bit deceptive because it's this big oval, but this is actually the entire night. This is kind of like the entire universe around us. So if you imagine that we are at the center of our observable universe, so we are not at the center of the universe, but we are at the center of our observable universe. The observable universe is the patch of the universe that has had time to send us information. This is limited by the age of the universe and the finite speed of light. So light does not travel infinitely fast. Light is the fastest thing we know of, but light still travels at the speed of light. It cannot travel any faster than that. So there's a fixed age of or a finite age of the universe. There is a specific amount of the universe we could theoretically have access to if we could see all of the light around us. The boundary of the observable universe is the CMB, because it is really the oldest light that we can have access to within the universe. So the CMB is kind of like our boundary between the observable and the non-observable universe. So when we see this here, what this really is the entire night sky. So in any direction you look in the night sky, you would see this. So we kind of have this sphere around us and we break it open and put it on this oval. So this is a two-dimensional projection of what is actually a sphere. So this is to say that every patch here on the night sky corresponds, so every dot here is a patch of the night sky. Now, of course, this whole image corresponds to looking 360 degrees. It is the entire observable universe, but projected 13, so we're considering a sphere here that has a diameter of 43 light years. Why 43 light years? The universe is 13.7 billion years old, but it is expanding. This expansion is accelerating. This means that this light year was produced when the universe was about 380,000 years old. By the time that light has reached us, that kind of boundary of the observable universe has traveled further away. So when we look at this figure, what we're actually looking at is the overall observable universe, a sphere of 43 billion light years. So that means that this is massive. This is a huge chunk of the night sky. So the question was, how do we compare this to like Laniakea or our network, which is a very, 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 very small chunk of the sky. So to do that, I actually want to break this down because this figure here, the CMB, covers a lot of every possible scale. You can break this into 4 chunks and you have 90 degrees of the night sky. You can break it into different amount of chunks, and each time, you can go to smaller patches of the night sky. So I just want to show you what happens if we actually plot out the CMB and what it looks like. And I am getting to the question. So this here is basically the fingerprints of the CMB. This is the angular decomposition. So what this is showing us on the horizontal axis is how big of a chunk in the sky we're taking, and the vertical axis shows us how many blobs there are of that color. And you can see that the average peak, that the biggest peak is at 1 degree. So we have this 1 degree thing in the horizontal axis, and this is where there's the big, big, big peak. So what this is telling us, let me just go back to the actual CMB figure. What this is telling us is that if we find the most common size in the night sky, that corresponds to about 1 degree. So pretty much all of these blobs, these individual blobs, are about 1 degree of the night sky. So this is when you take the entire night sky, you divide it into 360, you have 1 degree. So 1 degree on the night sky, but a really, really, really long distance away. So if you were to try to plot galaxies on this, it would be really insignificantly small. Now, I'm going to show you another image. I wonder if I have the right image here. So this is a very long and like hand wavy answer, but the point that I want to make here is that Laniakea, our local network, is a ridiculously small patch of the universe, really, really, really tiny. You would not see it on this night sky, on the CMB. It would just be a tiny, tiny dot. So how much of the CMB is Laniakea? Just a tiny, tiny, insignificant little dot. So I want to make this point a bit more. I'm going to show you the recent image we got from the Dark Energy Spectroscopic Instrument, which is this one here. So this is what happens when we try to look at, so every dot here is a galaxy. This was mapped by the DESI collaboration recently. Every glowing dot here is a galaxy. So Laniakea would be one of the tiny filaments that you can see here. One of these tiny, tiny, tiny filaments. Right, so it is just a very, very small patch. And you can, if you compare to the entire network, one galaxy, one filament, one of these strings is really small and insignificant in the grand scheme of things. Now, this here is just a fraction of the night sky that DESI, the Dark Energy Spectroscopic Instrument, has been able to map. So if we were to be able to map all of the galaxies in the observable universe, our galaxy would just be one dot among billions. And this goes further and further out. You can see, if you look in the background image, there's these two, kind of like the cheese slices going up and going down. And the zoom in is just on that tiny thing. And already in the background image, it's quite hard to disentangle individual galaxies. So this goes out, the furthest ones away here are about 12 billion light years away. Now remember that the CMB is 43 billion light years away. So if you consider, take that image you have in the back, multiply that by about 3 or 4 sizes, and then try to pick out one of the small filaments, and that's very, very small, but that's how it would look like on the CMB map. So to answer your question, if we go to the CMB map and try to put our galaxy there, you will not in any meaningful way notice it, because our galaxy, even our cluster, even our local neighborhood of Laniakea, is just one tiny filament in this massive cosmic web. And in order to match the scale of the CMB, you'd need a ridiculously big patch of the cosmic web. So how small is our, so I think the question was phrased as like, how big would we be? Yeah, how big of the area of the CMB would Laniakea be? We would be a speck of dust on that map. If I load this up again, Laniakea is a pixel in this map. You don't really notice it. It's there, but you wouldn't. The sizes are just vastly, vastly, vastly different. Hope that answers your question, John. I know my answer took a few digressions along the way, a few tangents, but yeah, the point here is that we are very small and insignificant, and our galaxy is small and insignificant, and our supercluster is small and insignificant, and the CMB is massive. So yes, just to give you an idea of the scales here, yeah, I think it's a very cool question. Thank you for asking that. I think it just comes back to the idea that the universe is mind-bogglingly big. And it's just so hard to think about just how big the universe is, because it's just ridiculously big. And when we look at the CMB, it's like, here's the entire universe. But here's I show this map, and it's like, here's a map of literally everything that existed in the universe 13.10 billion years ago. This map is the entirety of the history of the universe in one place. It is mind-blowing, it is big, it is ridiculous, it is amazing, it is very fun. Okay, there's a question here from saying, how does perturbation theory approach the hierarchy problem? Question for next week. As I said, next week will be entirely about perturbation theory. So I just wanted to tease it today, like this is what we're talking about next week. But the actual questions about perturbation theory, save them for next week. And we can absolutely discuss them next week, because there's a lot to discuss with perturbation theory. Something tells me that next week is going to be more than a 1 hour long stream. I am sure that I will not cover an introduction to perturbation theory in 1 hour. This is very good tea. For reference, this is white tea with blueberry. White tea with berries is literally the best tea. It is a bit late in the day to be drinking caffeinated tea, but don't tell anyone. I'm sure I won't notice it. I will absolutely have issues sleeping late. Anyway, another question here by Arlok. I never really understood, what is the sound horizon and how do we get the acoustic peaks in BAO spectrum? Love this question. I see there's another question here also by Arlok about CMB. As I was just talking about CMB, let me talk about CMB first, and then I'll go to BAO because they are connected. And there was this comment in between by Takina here. I think we need holographic technology to better convey this image better. Yeah, I think, but you get the image better now because of my explanation. Thank you. That is good to hear. Yeah, I feel like it would be very cool to have this kind of projected around you to get an idea of what we mean about this being the sphere around us. You can actually find like cool merch. Like at one of the biggest CMB conferences many years ago, people were given volleyballs or beach balls that had the CMB printed on it. I'm still very sad that I don't have one of those yet. I know where I might be able to acquire one, but I don't currently have one, and that is sad. Okay, sticking with CMB, we had a question here from Arlok. A general question on CMB. The photons that decoupled from the plasma, was that decoupling instantaneous or was it over the period of a few years? This is a brilliant question, really excellent question. And there's actually a lot of physics hidden in the answer to that question. So when I show this map, this figure, I always mention, there are protons, there are electrons, there are photons, particles of light. All three of these are bumping into each other. As the universe cooled down, protons and electrons could combine together to form neutral hydrogen. The photons at that point break away and start traveling freely throughout the universe. These are the photons that make up the CMB today, the cosmic microwave background radiation. And I always explain this like it's an instantaneous process. Electrons, protons combine together, photons break away, done. It is actually not an instantaneous process. It also didn't last a few years, but somewhere between instantaneous and a few years, like a couple months maybe. As the universe is cooling down, it just means that it becomes more energetically favorable for electrons and protons to combine together. So this reaction can start happening, but it is not instantaneously every proton and electron is like, okay, time to couple up, we're good now. It takes a while. It's a process that does gradually happen. The conditions have been met for this process to take place, but it's going to take a while. This is actually really interesting because when we try to explain the CMB mathematically, when we do our predictions, I showed you this figure before, and then I showed you what this looks like when we actually, was it slide 7? Let me see if I remember. I remember now. When we go to this one, like going from the image to this figure here and vice versa, going between these two requires perturbation theory, but also a lot of ideas about how this idea of protons and electrons coupling together, we need to know how this works. So something that is very important is, was this an instantaneous process? How slow was it? What happens here? And here we really get into nuclear physics, like what happens when an electron and a proton bind together? Is this an instantaneous process? What's the binding energy? What are the criteria we need for this to take place? So no, it is not an instantaneous process. In the grand scheme of the universe, yes, we can consider it to be instantaneous because if we consider 13.5 billion years of evolution, a process that's of, a couple of months, is not a big deal. But it is something that matters when we go down into trying to explain it, because, next week I'm going to tell you why there were some regions that were overdense, why there are some regions that are underdense. But there is a question of, does this have anything to do with the fact that this process wasn't instantaneous? And it does, because in regions where there's an overdensity, the energy conditions are going to be slightly different. So this binding together is going to be slightly different. It's going to happen at a slightly different rate. So it is absolutely not an instantaneous process. And trying to pick apart how that actually looks like is a really cool theory. It's a really cool thing to do. So I think that's an excellent question that you asked there, Alok. No, my answer is no, it is not instantaneous. It is definitely a slow question, a slow process. That is very cool. And there's a lot of effort, a lot of our understanding of the CMB required careful understanding of how quickly this process actually happened. So I feel like the CMB, understanding the CMB, you need to know a lot about cosmology, but you also need to know a lot about thermodynamics and a lot about nuclear reactions in general and how these things come together. So that is a very cool question. Thank you for that question. More CMB questions. I love that we're sticking with the CMB. I just saw that Fortanine came in. Hello, multi-universe people. Hello, multi-universe people. Whichever universe you're in, thank you for being on Cup of Cosmology. Okay. There's another question from John here, probably a question for next week, but I'd love to learn more about how Fourier transforms are used in cosmology. Let me put a pin in that question for now. Love that question. Love the technicality of that question. Sticking with CMB, I know there's a BAO and sound horizon questions. I am going to come back to those in a sec, but sticking with the CMB, we have a question from Bharat here. I know you've explained this before, but I still have trouble understanding how they know that the radiation observed is actually the CMB and not incidentally matching radiation from other sources. Brilliant question. So this is actually one of the biggest predictions we've had in our standard model of cosmology. So when we try to explain the history of the universe, like the area of the, not the area, sorry, the history of the universe, this is when I read comments and answer, and sometimes words from the question I just read pop into the question that I'm answering because brain can't multitask. Okay, so how do we know this comes from the CMB? Now, the best theory we have to explain the history and evolution of the universe is hot Big Bang cosmology, or the Big Bang theory. And the Big Bang theory is what allows us to explain basically these 13.82 billion years of cosmic evolution going from this initial singularity until today. And I just want to add a disclaimer here that some people say Big Bang cosmology, what bang, why are we calling it Big Bang cosmology? It doesn't explain the origin of the universe. And it never tried to. So the Big Bang theory is not about the origin of the universe, it's about what's happened since then. So we start our clocks after some initial singularity and we move forward with it. That is what the Big Bang model is. It's this explanation. So embedded within Big Bang cosmology, there is the prediction that we should have this background light, this background radiation everywhere in the universe. And this should have approximately the same temperature everywhere in the universe. So the prediction is for a pretty much uniformly distributed light that is at about a specific distance away from us, and it has the biggest thing is that it behaves like a black body. So when we look at light coming from a star is going to emit light in a specific frequency or in a specific range. This is why we get stars that, anytime you look at light, you get slightly different properties. But a black body is a body that emits at every possible frequency. And the prediction was within the Big Bang model, within Big Bang cosmology, there should be this background light everywhere in the universe at approximately the same temperature that behaves as a black body. Now, when we first measured the CMB many years ago, what people found is there's this background light everywhere in the universe at approximately the predicted temperature, and it is the most perfect black body we have ever measured. Getting a perfect black body, it's kind of the thing, like imagine I give you an animal and I ask you, what animal is this? And you're allowed to poke about with the animal and interact with the animal. If the animal walks like a duck, quacks like a duck, and waddles around like a duck, you'll probably say this looks like a duck. So when we predicted a light that is behind everything else in the universe at a specific temperature, that is a perfect black body. And then we observe a light that is behind everything in the universe at this temperature, uniform temperature. and is the most perfect black body we've ever measured, you kind of think like either this is the CMB or there's something else that is behaving remarkably like the CMB, exactly where we thought we'd find the CMB. So yeah, we call it the one. How do we know it is the CMB and not incidentally matching radiation from other sources? What other source could we have that would produce such a light? We don't have any other theories to explain what this light could be. So it matches our predictions, and it was something that actually observing the CMB, the cosmic microwave background radiation, actually really allowed us to kind of accept the hot Big Bang model as the universally accepted cosmological model. Before measuring the CMB, there were other possible ideas like the steady state solution, where you have a universe that is constantly producing matter and is kind of a static universe. But that one doesn't incorporate an explanation for the cosmic microwave background radiation. So measuring the CMB meant kind of like a key core prediction of hot Big Bang cosmology had been observed. So how do we know that it's this radiation? Well, it's exactly what we expected it to be, where we expected it to be, and it behaves how we expected it to be, and we don't have any other explanations for what it could be. So that's why we say that this thing that we've measured that looks exactly like what we expected the CMB to look like is probably the CMB. Hey Paul, great of you to stop by. I hope you had a good holiday. The picture you sent me looked amazing. Hope you had a good holiday, and thank you for popping by just to say hi. Always great to see you here. Moving into taxonomy streaming there, yeah. Yeah, it's like, if it looks like a duck, quacks like a duck, it's probably a duck. But humans are terrible at classifying things. Digression time. I was recently reading up about the duck-billed platypus. Why? Because. And I love that it's a mammal that lays eggs. Like, when we think about mammals, we think they are animals that do not lay eggs, they have fur. And then you get the duck-billed platypus that comes along and lays eggs, but still produces milk. Like, what is up with you, nature? What are you doing? Are you drunk? What the fuck is up with the platypus? Anyway, yes, digression there. I love it. Nature's amazing. I love how bad humans are at classifying things. We come up with systems, and then we find things that don't fit these systems, and we come up with new systems. Humans are very good at trying to classify things and label things. Nature just doesn't do that. Yeah, the exact comment I saw that started me down this path was mammals are a social construct in the same way as time is a social construct, and in the same way as gender is a social construct. There are things that we try to attribute to this, but it is a meaningless classification that we've come up with to try to make sense of the world. I love it. I love that there's an animal that I can pull up as an example. Anyway, digression. Big digression there, fandom. The comment here from Takina, cosmology is different to astrophysics. Yeah, they're both very much interconnected, but astrophysics really is studying the components of the universe, like galaxies and stars and how these things behave, whereas cosmology is like studying the whole system. And I think one analogy that I've called upon often is if you have an ocean, you can study the things inside the ocean, you can study the fish, you can study all the species, you can study the ecosystem, how everything works, or you can take the whole ocean and like ask the question of how does the ocean evolve, the currents, the flows, the cadence of the ocean. And that's kind of the difference, right? Cosmology takes a whole ocean and might not care about the individual fish living inside, whereas an astrophysicist would care more about the fish living inside. Of course, there's a lot of interplay between these because you do really need to talk to each other. You are moving through different scales. You are essentially looking at the same things but asking different questions. So they are different, but they are very closely connected. My master's degree was in astrophysics and cosmology, and then I specialized into cosmology. I feel like people who work in the field have a clear idea in their mind as to whether they're astrophysicists or cosmologists. But again, this is a category and people move between the two. But yes, they are different. And I wonder if you took that from the comment, from the prompt. If you did, great. I often put questions in the YouTube video just to prompt conversation. Consistently the last 3 or 4 weeks, someone has asked or commented on the questions that I put below. And I think the first one I put this week is, what's the difference between cosmology and astrophysics? So I'm glad, again, I'm seeing that people are pulling, either coincidentally, or people are reading the questions I put in the prompts that I put there, which is fun. Okay, now I want to go back to the question that I ignored just now about BAO and sound horizon. There was this question by Alok a while ago. The question was, I never really understood what is the sound horizon and how do we get the acoustic peaks in the BAO spectrum? Excellent. So BAO is baryon acoustic oscillations. So there is a big interplay between the CMB, the sound horizon, and BAO. So when we're talking about the early universe, where we have the protons, the electrons, the photons, we have two main effects. There's a lot of stuff happening, but we can narrow it down to two main effects. We have gravity pulling things inwards, and we have pressure pushing things outwards. Now, when we have baryons, the protons, electrons, and photons, the photons behave as radiation, the baryons behave as matter. So this means that you have things that can have friction between each other. Now, this friction term is going to push things around a bit. So you have radiation pressure pushing things outwards, and gravity pulling things inwards. And you have this kind of interplay. So if the universe was constantly at the same temperature, this would be kind of a system that expands slightly and collapses slightly. Pressure pushes things outwards, gravity brings it forward. You have this kind of cyclical, like almost like a breathing, like go out, come back in, focus on your breathing out. However, as the universe is cooling down, at some point, one of these two is going to win the battle. In this case, it's going to be pressure, and at some point, the photons break away. But you do have this interplay, and this is actually going to leave an imprint in the universe. Now, this interplay here, this kind of motion of going in, going out, going in, going out, this is actually going to leave an imprint. And this is what we call the acoustic oscillations in the early universe. We call them acoustic because they behave like sound waves in the way that the way the waves behave are very similar to how sound waves propagate. So we call them acoustic waves, but it's not actually an acoustic wave. And these acoustic waves are what then give us the peaks of the CMB. So if I had this figure here and I showed you we take the decomposition, we're left with this thing here. These peaks here, the first peak especially, is related to these acoustic waves, to these acoustic oscillations. Now, when all of this freezes out and this stops, you get what is known as the sound horizon. So the sound horizon is kind of like the last ripple before this stop, this kind of inhale, exhale type motion. When this stopped, there was a size that was left in the universe. This is what is known as the sound horizon. And the sound horizon is a concept that we can calculate from basic physics without knowing much about cosmology, just knowing how many protons there were, how many photons, or the ratio of photons to protons, photons to baryons. Knowing this ratio, we can calculate what the sound horizon should be. And then we can measure the sound horizon in several different ways. One of them is we take these acoustic peaks based on the height of the first peak or the kind of place where the first peak is, you can get a sound horizon. But this is also imprinted in galaxies, because as this expands and goes down, expands and goes down, these overdense regions in the early universe kind of get moved around. The overdense regions in the early universe is where we are eventually going to get the first galaxies forming. This means that if you have this kind of motion, when you get the sound horizon, you're going to have this sphere like an overdense region, and this is going to be imprinted in the universe itself. When galaxies form, they're going to form around this ring because this is where the overdensities are. Now, of course, you don't just have one ring, you're going to have multiple of them. I'm just going through my slides to see if I have the image that I want here. I'm not sure if I do. There is a very cool image that I have in mind explaining this. But as we have these kind of sound horizon things, these bubbles, this is a size that is going to be like the average size between galaxies. Now, of course, we don't just have one of these bubbles, we have thousands of them overlapped in the cosmos. So we're not just going to see a ring of galaxies, but we're going to see a lot of overlapping rings of galaxies. But this means that when we measure the average distance between galaxies, there's one number that we're going to pull out a lot more frequently than any other number. And that number is the sound horizon. I'm just, again, going through my slides here to try to find a specific image. There are many slides here. So, I just went past it. Okay, here we go. So what you can see here is an artist's impression of what this baryon acoustic oscillations would look like. We call them baryon acoustic oscillations because they're oscillations of the baryon fluid, and they left these acoustic waves. Now you can see here, this is an artist's impression where we have this ring, this sound horizon, imprinted multiple times. So when galaxies form, they're going to form all over the place. We're not going to see one individual ring. But when we calculate the average distance between galaxies, the radius of this bubble is a number we're going to pull out a lot more frequently than any other number. This number, once you've normalized it to today into the size of the universe, is like 147 megaparsecs over something, or just megaparsecs, sorry, it is a distance. So this is what is known as the baryon acoustic oscillation, and the sound horizon is the width of the last oscillation that was imprinted in the universe. Now, the reason this is cool is because this is something that is known as a standard ruler. Measuring distances in the universe is difficult because the universe is expanding, because photons get deviated by the gravitational force. It's very difficult to actually consistently measure distances. But if there's something in the universe that you can say this here is always going to be 147 megaparsecs, then it kind of provides a ruler. We know what the average distance between galaxies is in our local neighborhood. We know how the expansion of the universe works. So you can kind of map that to different places in the universe. So then you have a standard ruler that you can use to measure distances in the universe. So measuring the sound horizon, or this BAO scale, is really useful towards asking questions like how fast does the universe expand, which is not an easy question to answer, it turns out. So I hope this answers your question. I think it's a very cool question. There was the question that I'm answering, just to recap here. There's the question Arlok asked me a while ago of the sound horizon and how we get the acoustic peaks in the BAO spectrum. So the acoustic peaks and the sound horizon come from this interplay between radiation and pressure, or radiation pressure, and gravity. This leaves this kind of oscillation. It's imprinted in the universe. You can measure this in the acoustic peaks of the CMB and in the average distribution of galaxies. Vastly different redshifts at times that you're measuring. CMB is 380,000 years after the end of inflation, so 13 billion years ago. And when we measure the BAO scale, the baryon acoustic oscillation scale in galaxies, we're doing it in our local neighborhood. Which again, this is then something that you have as a standard ruler that you can kind of use to compare distances. Which is kind of cool when you think about it. I think that's very cool. So especially now when we do things like asking how quickly does the universe expand, this is something that turns out is really difficult to answer. We can use baryon acoustic oscillations to try to help us answer that question. So there is this artist's impression here that I think is really cool and really tries to illustrate exactly what we mean by baryon acoustic oscillations. And if we go back, I hope I got the number slide properly. Yes, if we go back to this image by Dizzy, the dark energy spectroscopic instrument, one of the biggest tools they use to measure the distance between galaxies is actually the BAO scale. So the dark energy spectroscopic instrument, which gave us this amazing picture here, is actually really focused on measuring the BAO scale, plus some other things, but mainly the BAO scale, and using that to map out where galaxies are. So I think that was a really, really good question that you asked there, Alok. It's really cool to think about how we measure the sound horizon. Hopefully that answers your question now. And if not, please do let me know. As always, if something is not clear, please ask again, and I will do my best to try to answer it again. Going through the questions, I know I'm quite behind on the questions, but I think I answered quite a few of those. There was a Fourier transform that I've pinned in my brain, so I'm going to come back to some of these. Let me just catch up with comments. I see that people did really like the whole conversation that I just went down about the platypus, which I always pronounce as platypus, but there's not a second L in that word. A comment from Prath: I remember seeing a t-shirt with a duck playing a guitar and a beaver playing a keyboard as two sets in a Venn diagram, and the intersection was duck-billed platypus playing a guitar. Yes, I love things like that. I see a follow-up here from Takina about the sound horizon. And Arlok, thank you for clearing up the doubts. Glad I could help, as always. This is the place to ask your questions. You can ask me literally anything. There are no stupid questions. Ask me whatever you want. We will try to understand everything together. Coming from Takina here. First time hearing about sound horizon, but it makes sense for there to be a sound horizon. It does. But you say imprint in the universe. Is that like an after effect that we detect? Yes, it is kind of like... So it's an effect that was left there before, and we can still measure. It's kind of like a footprint. If you see a footprint, you can say like this person was wearing a size 7 or whatever unit you're using to measure shoe size. So it's kind of like something that is there that we still see in the universe. It's something that is not happening today, but we can still see this effect. We can still see the footprint of these oscillations, and we use that to say, like, okay, this is a psi 7. This is 147 megaparsec. This is a distance that we can measure. While it's not an effect that is taking place today, it did leave this mark, and this imprint in the universe is what we measure. Okay, let's see. Going back to other questions. I think I've answered the CMB ones. I love that there were so many CMB and baryon acoustic oscillation questions. Those are always so much fun. Let's see. There was another question here that I wanted to go back to. Where was it? I love that I can scroll in questions. Also, I think now with the new setup, new camera, you can notice even more when I'm looking at the questions. Questions are on the right-hand side of the screen. My slides are on the left-hand side of the screen for me. So when I'm looking that way, I'm choosing a slide. When I'm looking that way, I'm reading comments. And when I'm looking up there, I remember where my camera is. So that now you can figure out, now with the bigger screen, I think it's easier. I just realized we are already 50 minutes in. Wow, this went by so quickly today. Ooh, I feel like I need to answer more questions quickly, because there's still some cool questions to answer. There's a question by John some time ago, probably a question for next week, but I'd love to learn more about how Fourier transforms are used in cosmology. Love that question. So Fourier transforms is taking something that is a time series and turning it into a frequency series, or vice versa, things like that. And it is something that we do in pretty much every field of physics and in pretty much every topic. So often you predict things to be at a specific frequency, but what you hear is a time series. I think an easy way to think about this is if I play a song, if I play a melody, or if I play a musical instrument, let's take a musical instrument, and I play specific notes for a period of time, you're going to hear this as notes over time. But you know that the notes are actually giving you a specific frequency. And there's a way you can convert from this kind of time data to the actual frequency the strings are vibrating in, if you're using a violin or something like that. Fourier transforms is something that we use to, when we do CMB physics, Fourier transforms appear. When we do gravitational waves, Fourier transforms appear. I think, so as someone who didn't like Fourier transforms when I was first exposed to them, I use them a surprising amount of time. So a Fourier transform is a mathematical object that allows us to basically map one thing into another thing. It allows us to convert A into B. And it is probably one of the things I use the most. So people who often ask me, what maths do I need to do physics? Fourier transforms is the number one. Derivatives and Green's functions, those three things, you can do most of physics. Those are the three things. But Fourier transforms, like specifically, I'm not going to go into details because it will get very math heavy, but yeah, we use Fourier transforms a lot and in pretty much every aspect of cosmology. But yes. There is a very cool question from James when we were talking about the CMB, and I mentioned these overdense and underdense regions, so these kind of fluctuations that lead to the cold photons and the hot photons, and I almost have it up again. I lost my CMB crisis. Here it is. So when we have here the hot regions and the cold regions, there was a question from James of, is there any reason for the denser area versus less dense, or is it understood to be random? So that is exactly the question that I'm going to address next week. Yes, it is random, but yes, we also understand that we know why it's random. We can explain it, and there's a lot more to unpack. But that is a spoiler for next week. So excellent question, James. Ask me next week, when the entirety of the stream next week is going to be asking the question, where does this come from? And we will also incorporate stuff about the sound horizon and BAO, because these oscillations that I mentioned, they have some connections and tie-ins to perturbation theory. Basically, if you want to do CMB physics, you do perturbation theory. So next week is going to be all of that unpacked. God, that sounds like such a streamer thing to say. Next week we unpack this. Next week an unboxing. Yes. At some point, yeah, I'm going to start doing like unboxing videos, unboxing my dark matter. Oh, look, there's nothing inside, I think. Anyway, I digress. Comment from John here. I've been thinking about what kind of material the universe as a whole would be like if we were the scale of the observable universe. Would it be something like an expanding foam, maybe like shaving cream? That is a very cool question. So the universe, as we know of it, is like 70% dark energy, 25% dark matter, 5% normal matter. The normal matter is mostly hydrogen and helium. So I guess you could think of it as a gas, and we treat dark matter as a fluid, kind of like a gas fluid thing doing its own thing. Dark energy is just like there. Would it be a foam? I'm not sure, but I think that is a very cool question. I'm not really sure what material, like what you'd see. Like if you could go outside of the universe, which is a philosophical question because you can't go outside of the universe, and you could poke it, what would you find? So there's a lot of people who study the early universe who talk about the early universe being like this quantum foam. So I guess the shaving foam is probably a good way to go. I'm not sure. I've never considered going outside of the universe and poking it with a stick to see what it's made of, but it would be cool if we could do that. But yeah, I think shaving cream could be, could also not be. Yeah, I feel like that's one answer. There's going to be many, but that is one answer. Okay, there was still some more questions that I need to answer. You're just thinking about Phineas and Ferb when I mentioned platypus. That is fair. Yeah, that is very fair. Sometimes I make random comments and people think about random things, and that is perfectly fine. You know, this is not a stream about platypus, but often on these streams there are fun facts with Diana. It's like, here's a random thing I read about. Also, if any of you follow me on Mastodon, I have 2 Mastodon accounts, one that I use for science outreach and one that I use for my inner thinkings. And my inner thinkings are usually like, here's a train fact, here's an etymology fact, here's random shit posting that should not be made public, but who cares, it's my social media. So yes, if you want to follow me on Mastodon, I recommend following my science outreach account. That is DCHooper91_Cosmo at astrodon.social. If you want to follow my private one, you can find it online, but I'm not going to advertise it because, especially over the last couple of weeks, that has gotten a bit out of control. But if you like etymology facts, that's where I'm putting all of those these days. Okay, the question, follow-up from Takina about the shaving foam. That was a cool question because on the scale of the small, mostly everything is empty space, yes. So if the universe is a material, I think it would have a material to it. Yeah, it would kind of be some material that is extremely empty. So I think foam, like bubbly foam, with that kind of sounds right. But yeah, that is very cool. Not completely sure, but it's a cool question. Okay, there was another question by Takina just now, about just now being 20 minutes ago. What more is there to understand? Like, what are cosmologists trying to figure out? I really desire to figure out how to travel to new planets, but interstellar space is such a death trap. Yes. So what more is there to understand? Well, a lot of things. I think this is really cool. Now, the first thing is, this is the composition of the universe. We have about 5% normal matter, about 26% dark matter, 69% dark energy. We get these numbers, again, from the cosmic microwave background radiation. It's not a coincidence that these slides are back to back. Now, we don't know what dark energy is. We don't know what dark matter is. We're very good at figuring out what it isn't. We have this general idea, dark matter is this weird type of matter that interacts gravitationally but doesn't interact electromagnetically, so it's basically invisible matter, but it's 5 times more abundant than normal matter. Then we have dark energy, which is this weird type of energy that is driving the accelerated expansion of the universe, and that's everything we know about dark energy. So, you know, I'm a cosmologist. My job is to understand the universe. There's 95% of the universe that we haven't yet figured out. So that is left to understand. Then there's also deeper questions. Why is there something in the universe instead of there being nothing? We know that in the early universe there was matter and there was antimatter. Every particle of antimatter found a particle of matter. These annihilated and destroyed them. You know, they met each other, they annihilated. If there had been equal amount of matter and antimatter, these two would have met, and today the universe would just be photons and nothing else. There would be no matter. Why was there more matter than antimatter in the early universe? We don't know. If we think about some of the particles in the universe, like neutrinos are part of our standard model of particle physics. We don't know how they have mass, or why they have mass, or what they look like, or if there's only 3 of them. That's another open question. There's also questions like, how do we fit gravity together with the other forces? We know how to explain the strong force, which glues everything together, the electromagnetic force, radioactive decay, or the electromagnetic force, electricity, magnetism. We know how to explain these at a quantum level. We know how particles behave when you put these forces on them. We don't know how gravity fits into this picture. That is another big open question. And these are just a few simple ones that come, like quick ones that come to mind. There's also things like how quickly is the universe expanding? Why is the universe still expanding? What caused the initial inflation? There's how is the universe going to end? You know, these are all questions that people try to answer. So that's a lot of what we're trying to figure out. And then there's also the incidental stuff that's going to come up along the way. It's kind of the thing of we don't yet know everything we don't know. And as we answer one question, usually you get another 5 popping up. So I think there's a lot of stuff that cosmologists are still trying to figure out and we are still working on. The day we figure everything out will be a sad day, but I don't think they'll ever get there because we learn one thing and we get 20 new questions, which is very, very, very cool. As to the second part of that comment, you want to figure out how to travel to new planets. Yeah, I think, you know, there is a lot of work being done on that, on like how we can actually try to become an interstellar species. Now, the problem is it is very difficult. It is really difficult to leave the solar system, to leave the planet, because humans have very much evolved to live on this planet. In this gravitational, with this gravitational force, you know, this amount of gravity, these nice conditions, these temperatures, this amount of lack of radiation because we have a nice atmosphere. You take humans away from our natural habitat, you know, the same with any species. If you take any species away from its natural habitat, it's kind of like, oh, I'm not programmed for this. I'm not designed for this. I don't know what to do here. If you take humans off of planet Earth with something like, I wasn't built for this. Where's my gravity gone? And then you add in things like, you know, we haven't yet got the technology to send us, we haven't yet sent people to our closest planet because the technology just isn't there yet. There are, again, a lot of people working on this. There's a lot of stuff happening in this direction. But it is a really, really cool question for like, how do we get to other planets? Will we do this within our lifetime? I think we will. I think within my lifetime, we will get someone to Mars. That would be cool. Although for caveats on that, see the previous stream that I did 2 weeks ago, because in the, you know, I'm an hour in because my voice is starting to go. In the last stream I did 2 weeks ago, we basically spent the entire hour and 20 minutes, discussing space exploration and ethical considerations and colonizing Mars and how we do this and experiments going on here on Earth to get us closer to that. So yeah, if you if you want a more in-depth discussion about interstellar travel, interplanetary travel, check out the stream 2 weeks ago. At some point, I should figure out how to link streams so that you get a nice pop-up here with a button you could click to go to that stream. Just never done that, but I could. But yes, check out the previous stream 2 weeks ago for more about how we can travel to other planets or what we're doing to try to get there. Okay, quick fire questions. Let's see, because we are 1 hour in. As you can hear, my voice is breaking. Just want to go through the questions again to make sure. I think I'd answered everything before we started talking about platypus. So I've reached the platypus part of the conversation. Let's go from there. Question from John. Is dark matter the source of gravity in the gravity pressure balance you're describing? It plays a role, but actually, when I'm talking about the sound horizon and the CMB and these acoustic oscillations, the main thing at play here is actually the baryons. So it's the baryons and the photons, because these are the ones that are interacting. Dark matter is there just pulling things in, but the main ones involved in these acoustic oscillations are actually the baryons and the photons, because these are the ones that are generating friction, so they can have these oscillations. You know, gravity is just going to pull things in, pull things in, pull things in. Gravity doesn't have the pressure to then do this oscillation part. So when we're talking about these baryon acoustic oscillations in the early universe, we're really talking about the baryons, so the protons and the electrons and the photons doing the radiation part. Because these are the ones that are interacting, these are the ones that have the friction between them. So these are the ones that really can do this interplay of go in, go out, go in, go out. So it's not just dark matter that I'm talking about there, but also the mainly the baryons and the electrons. Baryons, electrons, so baryons, which are electrons and protons, and the photons. Okay, there was a cool question here. Where was it? Yes, by Fontanine. You know, I pull all of your names based on the usernames, and I just take part of that. If I mispronounce any of your names, or if you want me to call you something else, please just write it in a comment. Sometimes if you have a long name, I just pick out part of it and say that. if I ever call you something that you don't want me to call you, please just tell me in a comment and I will change it in my mind. There's not a problem. I'm just going based on usernames, but if you have a preferred way you want me to refer to you, just let me know. I try to keep note of all of my regulars. So let me know. For now, I'm just like pulling out usernames, but do let me know if you want something else. Question from Fortunine here, which just prompted that. I've heard that if you could describe an overall sense of the universe, it would smell like a terebinth tree. Huh. I've never heard about that. That is very cool. I like the idea that the universe might smell like a giant tree. So if we were outside of the universe, back to our hypothetical scenario, we're outside of the universe, we have expanding shaving cream that smells like a tree. That is a nice description of the universe. Where do you live? I live in a universe that is made of shaving cream and smells like a tree. Yeah, that sounds cool. I had not heard that, but that sounds very cool. I'm going to look into that. Why does the universe smell like a tree? Why? Universe tree. I'm just writing down universe tree, and I hope that I remember what that means afterwards. But that is cool. That is. I'm just going to add universe smells like a tree actually, because else I'm going to be very confused when I look at my notes later. I had not heard that, but that is very cool. There is a thing that scientists at some point figured out the average color of the universe by taking basically all of the light we know of in the universe, all of the stars, and kind of taking the most common wavelength and averaging it out. And the color they came up with is like an off-white creamish color that is actually called the cosmic latte. So if you search for cosmic latte, that is the color of the universe officially. It's like an off-white creamy color. Also, I've mentioned a few times I've dropped hints about a second or another outreach project I have ongoing that you will hear about soon. Just fun fact, our base color scheme for that other project is based around Cosmic Latte and colors that match onto Cosmic Latte. It's going to be a small Easter egg that I've just told you, but when we're done with it, when it's ready, when it's out in the world, you'll notice there's an off-white color, and that off-white color is exactly Cosmic Latte, chosen intentionally. I know that still doesn't tell you literally anything about my other outreach project, but it's a hint. And coming soon on Cosmic Scales. I'm going to keep it vague, but yeah, coming soon on Cosmic Scales. Okay, let me just catch up with questions, and there's still one or two that I still need to answer, but yes. Okay, let's see, going back to where was I in the chat, we're going to do another like 5-10 minutes, wrap up the questions, and then we're done. We just got distracted by the universe smells like a terebinth tree. I love that. I'm currently blanking on what a terebinth tree is other than type of tree. I'm very bad with tree types and bird types, but that sounds so cool. I love that. Okay, we were talking about the universe being cosmic foam. Comment from Prathia, why doesn't normal energy show up on the matter, dark matter, energy pie chart? I love this question. This is a complicated question. So anytime I show this pie chart, there's dark energy, dark matter, normal matter. What about normal energy? Now, normal energy, we know through Einstein's E equals mc squared. Einstein gave us this nice formula here. Energy equals mass times the speed of light squared. So technically energy is there because anything with mass can be converted into energy. So when we talk about the energy of the universe, the normal energy of the universe, it is basically everything with mass. Now, dark energy, the name dark energy is not necessarily accurate. Now, we can see energy in the universe as being kind of like a byproduct of something happening. Something has mass, therefore it has energy. Something is moving, therefore it has energy. Dark energy is actually like a whole new component, a whole new species. Calling it energy is perhaps not the most accurate thing to do, but we call it energy because it behaves, the way it moves through space-time is the same as how energy moves through space-time. So the way it dissipates, the way it moves as the universe expands, behaves a lot like energy. But it is not energy in the same sense. Like we know that we can convert matter into energy. We have E equals mc squared. We know that energy describes a property that everything has in the universe. Now, dark energy, on the other hand, is a component of the universe that behaves like its own liquid fluid thing in the universe. It affects the evolution of the universe. It is not an intrinsic property that everything else has. It is a new component. And we call it dark energy, which is a bad name. We should actually just call it like repulsive force would be perhaps a better name. But then we run into the problem of, is it a force? How do we relate that to the other forces? But yeah, we call it dark matter. It is not dark. We should call it invisible matter. And dark energy should be like this repulsive thing. So we call it energy to make it clear that it doesn't behave like matter. The way it behaves is like energy. But dark energy is not equivalent to normal energy, but in the dark sector. It is a different component to the universe. It is not a property that things have. But yeah, this comes down to a slightly badly named things, which is a common theme in science. We're really bad at naming things. So dark energy is actually not directly relatable to normal energy. It's also confusing because we know E equals mc squared, so it's fair to ask, if we applied that to dark matter, do we get dark energy out? No, they are really different things. We just call it dark energy because of the way it moves throughout the universe is very much like an energy, but that doesn't necessarily mean it's the same as energy. Hope that answers that question, but I know that's convoluted. My answer was convoluted because it's a very difficult question to answer. Hopefully that provides a somewhat hand-wavy answer. Hey, Gwadaf, great to see you came in at the end. Don't worry, I'm going over time, so that's fine. Going over time doesn't matter whenever you come in. And if you missed everything, you can always watch the replay. The replays are always up on YouTube. They're up on Twitch for 2 weeks. If you miss it, you're always welcome to go back and watch it. And leave more questions. I do get notifications when people leave comments on my videos. So if you watch this in 10 days and 2 weeks and you have a question, pop it in the comments. I do try to get back to people. Often when people ask questions in the YouTube comments, I leave an answer. If you write nice comments, I often reply or at least thumbs up you because thank you. If you leave a nasty comment, I often just delete it because honestly, life's too short. So yeah, feel free to leave a comment whenever you're watching this. Comment from Scott. Recently, I was chatting with a stranger at a bar and he was astonished at how much I knew about cosmology. It's because you've been watching me for nine years. Yeah, thank you, Scott. I'm glad that you know cosmology and you think of my streams. Some of you have been here 9 years. Some of you have been here, it's your first time. However long you've been here, welcome. If you learn one thing from watching my streams, that's great. If your takeaway from my stream is that the universe is cosmic shaving foam that smells like a tree, that's great. You can back it up. If in doubt, point to my videos. So I'm very glad that you feel like you've learned cosmology with me. That is the point of these streams. So job well done. I can pat myself on the back for that. I got James here put a comment saying I'm perturbed already whenever I mention perturbation theory. Yeah, honestly, that is a joke that I made frequently during my PhD on perturbation theory. I was very perturbed. It's a joke that I still make. I'm still amused by it. Yes, I'm deeply perturbed by perturbation theory. Hopefully next week we will unperturb people. I will make you slightly less confused about perturbation theory. That's going to be next week. Coming from Guadav here, or quote from Douglas Adams, the story so far. In the beginning, the universe was created. This has made a lot of people very angry and been widely regarded as a bad move. Yes, excellent opening line to an excellent book. Okay, froth milk is better, I think. Rather, I'm not sure if that is better than shaving cream or better than the cosmic latte. In either case, as someone who doesn't really like milk, and we already have Milky Way, let's not throw too many milk things. I'm going to stick with shaving cream and cosmic latte. Yeah, the comments here, people laughing at cosmic latte with reference to Earth, like, yeah, so it's like based on our own perception of colors and how we've defined colors. If we take the average color of the universe, then we get the cosmic latte as a color. And yeah, I see there were comments here, people saying cosmic latte is fantastic. So the universe is a shaving cream that smells like a tree and is an off-white latte color. Yes. And then John was actually the first one to say maybe it's frothed milk instead of shaving cream, and that's why we lead into cosmic latte. Yes. I love that you're all very amused by the cosmic latte. Yeah, it was very funny when I first saw that. I was like, the universe has a color, and that color is kind of beige, creamy. It's not an interesting color, but it's a cosmic latte. We call it cosmic latte, and that sounds good marketing. We did. That's once where we were good at naming things. Cosmic latte. You can find the hex code for cosmic latte online if you want to throw it as an Easter egg. I'm not sure if it. No, it is not in the Cup of Cosmology, or at least not intentionally. So that is not an Easter egg yet, but it will be for my next outreach project. Okay, I think there is one more question that I need to address or comment that I need to address, and then I think we should be done. Comment from Takina here. I'm keeping in mind that every term we use is a social construct. Yes. So like dark matter isn't dark matter, and so is gravity not gravity from my understanding. Gravity is space. And yeah, it's the thing, like every model is wrong. It's good to a point. Every descriptor is valid to a point. And humans come up with these words, these classifications, these things just to try to give meaning to the world around us. Sometimes we're good at classifying things, sometimes we're not. Sometimes we come up with names that have meaning for a long time and that make a lot of sense, and sometimes they don't. I think this goes back to, we can go back to why do we know the CMB is the CMB and not something else? Well, it looks like the CMB, behaves like the CMB, we call it CMB. We've come up with something that we've defined as gravity. If it behaves like gravity, we call it gravity. There's a fun Easter egg, you could call it Mavity instead. For the Doctor Who fans out there, it doesn't change what it is. But yeah, the classifying things like what is a planet, what is a dwarf planet, what's the distinction between them? This is something that often there are debates that are more etymological and debates that are actually more meaningful. And when we try to classify the world, we are always going to make mistakes, but they provide us with a good framework to understand the world. So yeah, gravity is our best description we have so far about gravity. Dark matter is the best description we have so far about dark matter. But yeah, we can really get into some very philosophical conversations about why things have the names they do and how they're named. And I think that's very cool. And we could have gone with froth milk instead of shaving cream, but I do like to think that the conclusion of today's stream is that the universe is shaving cream that smells like a tree and is an off-white cosmic latte color. That is a nice picture. If there are any artists in the room, please feel free to draw this, this shaving cream in a specific color that looks like a tree. I feel like that would be a very funny thing to have. Definitely not something I'm going to draw, but that is a very fun concept. Okay, I think I've addressed all of the comments. Only took me an hour and 17 minutes, and we had plenty of appearances of my favorite image today, the cosmic microwave background radiation. This is the best image, and we had plenty of appearances today. I think I lost count. For the people who are new here, there's the ongoing joke that I am incapable of doing a cosmic stream, a Cup of Cosmology episode without the CMB appearing. Today, you definitely got plenty of appearances. Next week, where we're unperturbing perturbation theory, we're unboxing perturbation theory next week. There will definitely be plenty of CMB appearances next week as well. There's a final comment here from Guadav that I realized I hadn't addressed about the cosmic latte. I assume the average color will be different at different points in the universe. Yes. This is very much, from our perception, taking all of the light that reaches us, kind of smearing it all out. This is mixing all the lights we receive in the universe together. You end up with cosmic latte. But yes. Okay, thank you everyone for all the questions and comments and digressions and tangents and fun conversations. This has been really, really fun. I like that we had a couple of new people in here. Alok, Takina, thank you for your questions and your comments. It's been really fun. For all of the regulars, for anyone here, for anyone lurking and not commenting, thank you for being here. Really, I'm going to say this again. Cosmology is heading into its 9th year anniversary. And Cup of Cosmology is here because everybody comes and interacts every week and asks me questions. And anytime I do an Ask Me Anything, I never know what direction we're going to go in. It's up to you. And every week I finish like, wow, got some really cool questions today. That was fun. That was really fun. I love talking about science. I love talking about cosmology. And I love that you all come and ask questions. If you've been here for 9 years, if it's your first time, thank you. Thank you for being here. Thank you for asking your questions. It is really, really fun. Yeah, Cup of Cosmology will be online next Sunday. That is just 1 week from now. One week from now, next Sunday, where I will be talking about perturbation theory. We're going to figure out where the CMB comes from, why there are galaxies, how these are connected, and how quantum physics might have the answers. Wow, I'm getting into the tune in next week clickbait titles, but yes, that is what is happening next week. I had to throw in the word quantum, but we will actually cover that as well. Next week, same time as always, that is 8 p.m. if you're in Finland, 7 p.m. if you're in the rest of mainland Europe, because Finland's an hour ahead. 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US. As always, there is a time zone converter on cupofcosmology.com where you can figure out when the next stream is in your own time zone. That is cupofcosmology.com. There's a big time zone converter where you can click and figure out when the next stream is. Also, you can subscribe to the YouTube channel or to Twitch, and then you'll get a notification half an hour before I go live so you can't miss it. I hope you all come next week with good questions like you did today. It's been great fun. So many cool questions. Thank you, everyone, for joining. This really, really has been a lot of fun. I hope to see you all again next week, same time as always. And I hope in the meantime, you'll stay safe and take care of each other.